Hello everybody, my name is Hooman Rezaeian, a PhD student at the University of Auckland, New Zealand. The title of my presentation is a comparison between cyclic and monotonic behavior of composite diaphragm interfaces under high shear force. My presentation consists of the following parts: introduction, test program, then I'm going to talk about results, conclusion, and acknowledgement. Lateral loads caused by an earthquake transfer from diaphragms to the lateral load resistance systems, which then transfer these forces to the ground and foundation. So providing a dependable load path from the diaphragm to the seismic resistance system is essential, and this should be well designed and constructed. And actually the integrity of a structure is highly dependent on the performance of its diaphragm. Composite metal deck is one of the most popular floor system in the world. It consists of the profile steel deck with a concrete topping and mostly welded mesh reinforcement as shrinkage and temperature reinforcement to control cracking. Composite action between the concrete and the steel deck is provided by embossment, and composite action between the slab and the beams is achieved by shear connector like shear stud, high strength bolts, or channel shear connector. So this study determined the seismic behavior of composite slabs, focusing on the interaction between these slabs acting as diaphragms and the lateral load resistance system. So here we can see the schematic of the test setup, the slab, reaction beam, and the loading beam. So the slab was designed in a way that this test setup was designed in a way that the slab was under pure shear. This is achieved by preventing the slab from twisting. So 4 buttresses were constructed and placed on both sides of the loading beam to prevent the slab from twisting to apply pure shear. Here you can see the general view of the test setup. This is the slab. We had a reaction beam bolted to the strong floor. Loading beam was connected to the actuator. We had a data logger, actuator controller, and one camera was placed on timber frame to take photo during testing. Another camera was under the slab. 4 buttresses, as you see, were constructed and placed on both sides of the loading beam. And as you see, the specimen were instrumented with LVTs and displacement gauges to monitor displacement and concrete strength. And PTF fishes were placed on contact surfaces to reduce friction between the loading beam and buttresses. And also you can see the loading beam was seated on steel rollers, so it could move easily. 3 different and encouraged details were investigated. The first one, as you see, rib orientation was parallel to the supporting beam. The second one, rib orientation was perpendicular to the supporting beam, but it didn't continue over a top flange to make a concrete beam along the reaction beam. This is more common in New Zealand, and for a third specimen, rib orientation was perpendicular to the supporting beam and it continued over the top flange. So 3 specimens of each detail were constructed and tested. The first specimen of each detail tested monotonically, and the second and third one tested cyclically. So as I said, 3 specimens were tested monotonically. Here you can see the in-plane low displacement response of 3 specimens. All 3 specimens exhibited approximately the same behavior, and the ultimate shear strength of 3 specimens were around 550 kilonewton, but these ultimate load appeared at a slightly different displacement. And as you can see, the first one exhibited the most brittle behavior among them, with a sharp drop in loading carrying capacity. Here you can see the stop motion video of testing the third specimen. In practice, it took like 3-4 hours. And here you can see the cracking pattern and failure on reaction beam. Here is a reaction beam, and this is a loading beam. Yeah. So then a cyclic loading procedure was established based on the monotonic test and used for the rest of the 6 specimens. 100 kilonewton considered as the first target load, and then increased by 100 kilonewton for the following loading steps. And so based on the monotonic test, around 280 kilonewton was understood as the yield point when diagonal cracks initiated to form. So 3 complete cycles were applied at each load step. Therefore, 6 complete cycles were within the elastic range, and then tests continued to capture cyclic deterioration of specimens. And so from these tests, hysteresis curves obtained, and so backbone curves were plotted for specimens. So this is an efficient method of evaluating the results of monotonic test and cyclic test, and we can compare them easily. So here you can see the result from the monotonic test, red lines, and also result from the cyclic test. These are backbone curves for a cyclic test. And as you can see, there is no significant difference between the monotonic test and cyclic test in the elastic range in this part. And all specimens exhibited approximately the same elastic in-plane response, but you can see that cyclic loading resulted in lower ultimate strength, around 15%. Also, a slippage of specimens were monitored during testing. So 4 displacement gauges placed on 4 corners to measure slippage between the slab and the supporting and loading beams. Here you can see the result from the monotonic test and cyclic test. As a result, again, you can see that the similar behavior we can see in elastic range. There is no big difference. But after yield point, we can see that the cyclic test resulted in just a little bit greater slippage. But all slippage for monotonic test and cyclic tests were smaller than 0.7 millimeters, with an average of 0.2 millimeters, indicating that a fully composite action between the composite slab and the supporting beams was existent. And even after a yield point, we can see just a very small amount of slippage. And generally, monotonic and cyclic tests resulted in almost a similar response. A comparison between the test result and codified equations from New Zealand standard, Australian standard, and European standard has been made, and these standards could accurately predict the design shear strength of the first and second specimens, but they overestimate the design in-plane shear strength of the third specimen. With rib orientation perpendicular to the supporting beam. Based on the test result, the contribution of the steel deck and shear stress in shear strength of composite diaphragm is negligible. Very briefly about conclusions. So all 3 different specimens tested monotonically reached the same ultimate shear strength of 550 kilonewton, when the counterpart tested cyclically touched 480 kilonewton, resulted in approximately 15% lower ultimate shear strength. In the elastic range, the load displacement behavior of specimens under cyclic loading was found to be similar to those of the monotonic test, with the backbone curves being very similar, and slippage of specimens was found to be insignificant in the elastic range, and even after that, a very small amount of slippage was measured until the specimens reached the ultimate shear strength. Finally, I would like to thank everybody who helped me and supported me to do this study, and thank you very much.